Hey everyone, no teaser today. I couldn't find my video clip when it was time to go live, so we're live. That's it. Usually you're probably getting used to those 30-second countdown. No such thing today. We are live. It's 1 past the hour. We're going to start collecting people. While we are doing so, let's do, you know the gig by now. Who's on, basically. So I'm Benjamin. I'm going to be your host for today. And we have Javier already saying hi. Where are you joining us from, Javier? It's going to be an interesting discussion today. Demos, always demos for those Zephyr Tech Talks. We're going to talk about all things robotics. So I'm actually really looking forward to this one. There's there's been some interesting developments in the open source, open hardware, and robotics world over the past few years. You may have heard about ROS, the robot. I think it's robot, not robotics. The robot operating system, which is pretty interesting beast, which is used, as far as I can tell, in things like smart, like Roomba and things like that. They use ROS to orchestrate and to basically drive the robot. It turns out that it's also something that makes a lot of sense to run in constrained devices, right? It doesn't have to be big robot arms and industrial machines. So we have people joining us from Munich, from the UK, from Paris. Without further ado, I guess I can bring our speakers and guests on to get the ball rolling. So we have Dave, we have Steve, and we have Brad, all joining us from where? Where are you guys joining us from, actually?
I'm in Boston.
I'm in the suburb of Boston.
And I'm in northern Vermont.
Nice. So tell me a bit about who you are, basically, and what got you into ROS/robotics/ I think, we're going to cover tons of topics today.
Brad
Zephyr,
thought it was a good idea.
Yeah. It's going to be a lot of fun. So let's start with Dave.
Yeah, so, we've been doing embedded stuff pretty much all along. And our presentation, we'll go into a little more detail about that, but we're basically an embedded software design firm. And we had also recently been doing some work with Amazon in their robotics department. And we've been very interested in Zephyr just because I think all along, embedded Linux is great for embedded stuff when you have enough resources, when you have enough power, that kind of thing. But I think all of us kind of felt, there was still this need for something for small devices. I think a lot of us came from the RTOS world, back when people used VxWorks, and people still use VxWorks, I guess. But PSOS and VxWorks were once the kind of primary ways you did embedded systems, and then Linux came along and took a lot of that market share away, and that was great. But you still don't. It's not easy to run a Linux system on just a small battery powered board and something really memory constrained. So that's what got us into Zephyr and micro-ROS. It looked interesting because micro-ROS actually brings the ROS, which is a pretty large software package that only will run on kind of larger embedded systems. It brings it down into the microcontroller world. So that's kind of it in a nutshell.
Yeah. Okay. So maybe as a way of introducing everyone, Steve, maybe do you want to tell a bit about yourself?
Dave covered most of the recent details.
But yourself, like
I know.
Right?
I've done a variety of things like compiler design, computer language design, front-end and back-end applications, mostly back-end, and then joined Beechwoods and got into the embedded software world. And now we're looking at the applications in the robot environment and distributed IoT applications.
Okay.
That's pretty much it for me at the moment.
Sounds good. Brad?
I've been at Beechwoods for a long time. But as we were working with people, I was looking at the thing. One of the things I saw out there was those great big round mirrors that cars used to see in hidden driveways, things coming at them. And I was thinking, how would that work in robots? Because robots can't see the mirror. They can see a round object, but not the content. It would be great if you could put a little tiny microcontroller there that would tell the robot that, hey, there's a truck coming at you. And the only way to do that is to use micro-ROS. So we started the development, and I asked the guys to build the Pico W, because we had a bunch of them, and I was using ESP32s and ESP32C3s because I wanted to be as small as possible. So that's how we got into this.
Awesome. Yeah. So let's bring. I'm going to put your slide on the screen, and maybe you can. I mean, I can tell you what I'm interested in learning myself. So I've been playing with ROS and micro-ROS in the past. I certainly, and I hope, and I'm pretty sure you will be sort of doing a refresher of what it is all about, and like what's the difference also between full-blown ROS and micro-ROS. I would love also to understand more about the sort of the maturity of the ecosystem, because I mean, like I said, and I'm pretty sure there's literature out there of companies that have been vocal about where they've been putting ROS in actual commercial products, including things like smart Roomba sort of robots. But micro-ROS, I'm not so sure myself, like where it's at. So yeah, we'd love to understand more of that. And I'm sure there's also folks watching us that either come from the Zephyr side of things, maybe some come from the ROS and micro-ROS side of things. So please make sure to ask questions, basically, like put questions in the chat, whether you're joining us from LinkedIn or YouTube. We will be happy to take the questions as they come. So yeah, Dave, why don't you take it away with your slides and hopefully demo as well?
Okay, sounds good. So do I have control of this? I need to. So just a brief. So the presentation demo today. This is basically what we're going to do. We're just going to tell you a little bit about ourselves, which we already kind of have, and give you an overview of ROS and micro-ROS and ROS2. We're going to do a little demo just of what ROS can do at the infrastructure level, and then talk a little bit about the war stories in building micro-ROS, and show some code examples, and also talk a little bit about running Wi-Fi with Zephyr on the Pico W, which is something kind of new here, and coming along. And also a big part of this, the Pico W actually uses something called a PIO, a programmable I/O controller, which is a special feature of the RP2040. The Pico W's Wi-Fi module uses that, and we found it useful for other things too. And so Steve's going to talk a little bit more about that, and then we'll have a Q&A at the end, of course. So just a little bit about Beechwoods ourselves. We are a full-service embedded software design firm. We do everything from coding to architecture, integration, development, and deployment, and long-term maintenance of embedded software products. And we were founded in 2005, so we're pushing almost 20 years now. We work with a variety of different customers, some pretty small, some pretty large. The first customer was DirecTV, and even through acquisitions and everything else, they're still one of our customers 18 years later, so we're pretty happy about that. So overview of ROS2 for anyone who's not aware. I'm going to kind of use ROS2 and ROS interchangeably. There was once a ROS1, and you can go read the history if you'd like, but basically ROS2 is ROS now. Everyone's using ROS2. And it's an open source communications infrastructure package for robot components. It's the thing that makes it really specialized for robots, I think, is that it's got just this huge ecosystem of packages to support all sorts of robot components: sensors, actuators, motors, battery, control LiDAR sonar. You can read the whole thing, but there's like 2,000 packages out there, so it's got lots of support, and it's become a kind of a standard in the robot world. In terms of communications and messaging infrastructure, it basically provides both a kind of a traditional client-server request and response type of interface, as well as a more of a pub-sub, publish-subscribe type interface, like you may be used to MQTT, but MQTT is not necessarily adapted so well for robots. It's text-based for one thing. But it was a similar type of functionality. So you see that in the diagram here. The terminology that they use within ROS is pretty similar. The only thing that might be a little different is ROS kind of has a special definition of what a node is, which is basically just an entity that provides information via one of these interfaces. ROS uses a DDS, which is a standard for messaging. Allows you to define your own. It has a lot of pre-built data types, but it also allows you to define your own using a language-neutral interface definition language. The fundamental building block of a ROS system is node. Everything is made up of nodes in the ROS world. I guess I already covered that. We have the pub sub and client service, and I guess most people are probably aware of the differences between these. But one of the biggest differences between a pub sub and a client server interface is that publish and subscribe is many to many, whereas a client server interface is usually a one to many. There's only one service and maybe many clients, whereas publish and subscribe, anybody can publish. You can publish your data to anybody else, and anybody can subscribe to the data and also be a publisher themselves. So it's more of like a peer-to-peer type of arrangement. ROS2 also is popular because it provides APIs for a lot of different languages. I think C++ and Python are probably the most popular. So that brings us to micro-ROS. And so despite all the great things about ROS, it's kind of large, especially for those of us who, I assume this audience is a lot of people who are interested in Zephyr and the kind of microcontrollers that we use with Zephyr, where you may have only kilobytes of memory rather than gigabytes, and you may be lacking in storage and that kind of thing. You're just not going to fit a ROS2 system on that small of a board. We've kind of determined, for people who are familiar with the Raspberry Pi line of single board computers, you pretty much need like a Raspberry Pi 4 to even think about running a ROS2, and you may even want to try to get your hands on a 5. So that's fine for a lot of things, especially robots. Big robots may have, they probably already have lots of power because they have these big mechanical motors and things like that. But there's also components of a robotic system that are sometimes small sensors that may need to just run on very limited power or batteries and be remote, that kind of thing. So that's where micro-ROS comes in. Micro-ROS, it can easily fit on most of the Zephyr boards, at least the ones that support Wi-Fi. It's just much smaller all around. They get around that by using one of the ways they do that is by using a special version of DDS called DDS XRCE. And kind of the fundamental difference between using micro-ROS and using ROS2 is that to use micro-ROS, you do need at least one ROS2 host that's running an agent, and so that needs to be like one of these larger single board computers that can run ROS2. The idea is that the micro-ROS devices can all connect to the agent and proxy through the agent. And once you've got that arrangement set up, the micro-ROS devices look more or less like another ROS device to everything else that's in the ROS system.
There's a question that I think we should take, if you don't mind. You sort of hinted at the fact that ROS doesn't use, does PubSub, but not necessarily with something like MQTT. Timon is asking, if you can share maybe if some more details with regards to the way it's done in ROS and in DDS, and why basically MQTT wouldn't be a right choice. I think we're talking about things like more advanced QoS levels, for example, right? And like just basically throughput, I guess, and making sure that you can put more on the wire than you would be able with MQTT. Is that the gist of it?
Well, I think it's. I mean, one thing, as I mentioned, is that there's this huge ecosystem of packages that work with ROS, right. But also it is a binary protocol, so it can, I think, be inherently more efficient, more real time than MQTT might be. It's I suppose a valid question. I'm sure there's some situations where you probably could certainly. Some of the things, the more simpler things we're going to demo here, you'd probably get by with using MQTT, but I think,
it's more like if you want this package that automatically eats data from a LiDAR and turns it into an actual map, then it already exists in the ROS ecosystem, right? And it just works.
Yeah, it's already there.
Yeah, those kind of things, right?
Steve said he can give a more detailed answer, so maybe we'll pass on to him.
Yeah, sounds good. Yeah, and Steve, do you want? Let's bring you on stage. There you go.
Not exactly detailed. The way that ROS is set up, there's a central coordinator that there's a master that sets up and arranges the communication channels. It's basically a way of finding who you're publishing
right.
to. The topic.
It's like routing, almost like optimized routing.
But what it does, it sets up direct channels, peer-to-peer channels, so they can communicate via UDP or a serial line or TCP, whatever is appropriate for your configuration. But that lets that be much more efficient because you're just speaking directly at whatever network.
You have to go through a broker, basically, is what it is.
Yeah, that makes sense. Yeah, and I think that probably addresses another question that came on LinkedIn. Someone asking how reliable the communication can be, and if there's a deterministic request response latency. And I think this touches
as reliable as
yeah, And so Timon says, maybe it's a bit like peer discovery in a protocol like BitTorrent, where the tracker only lets peers know about each other. Probably like there's this kind of, and we're going to see that in the demo actually, right? Like the sort of auto discovery of the various nodes and the master knowing about what nodes come online and offline. So I guess it's a bit similar.
Right. Yeah. So one thing I want to mention about another thing I want to mention about micro-ROS is that you can use just about anything for your transport. We're gonna, in our demo, use all UDP over Wi-Fi, but they have CAN packages set up that will let you use serial or BLE, and there's also hooks where you can just define your own. So that's pretty flexible. One thing about micro-ROS versus ROS is that the API right now is mostly limited to C language. I don't think that would scare too many Zephyr developers away, but that is kind of one limitation right now. It's funny, there is actually C++ in the implementation that you'll see when you build it, but the API right now is mostly C. I suppose C++ is probably possible. Python, I don't know about Python and Zephyr, but there is MicroPython, so who knows, maybe that's coming for it. So here's kind of a diagram of one ROS, micro-ROS client and how it interacts with the ROS2 agent. This wasn't my favorite diagram to kind of give an overview. It's good for what it is. This is actually pulled straight from the micro-ROS documentation. What I would have liked to see is it show the multiplicity of micro-ROS devices, and also you could also have mini ROS2 stacks as part of this whole system. So this is just showing, the one small part of it, but basically shows you where the DDS client lives, and the adapter, and your middleware, and the API, and then your application components up here. Probably most of what you'd expect to see from a stack like this. And then going through an RTOS, you don't actually have to use micro-ROS with an RTOS, and that's going to be a little bit relevant, and one of the things I explain while when I'm showing the code examples. But I think I like working in an RTOS whenever possible. So, but it is small enough that it's designed to even work bare metal if you wanted to. So now I'm going to turn on my camera and show you the setup I have here. So I have a couple of micro-ROS devices that are basically acting just as temperature sensors and pressure sensors and light sensors. I have one outside my window. It's about 5 degrees Celsius, about 40 degrees Fahrenheit. Hopefully that conversion is about right. I'm an American, so I don't haven't quite got a grasp on the intuitive.
The only thing I know is that minus 40 is the same in Celsius and Fahrenheit, right?
I do know that much, yeah. So anyway, I've got these two devices, and then at that point, we should probably switch over to my desktop, where I'm going to bring up a UI. Now this UI is running, so I guess I should, to start with, I should explain that we are running the agent on an AWS cloud machine. So as we explained in the beginning, all the members of this team are in different places, and so we all wanted to share one agent, and so we just put a machine up on the cloud.
So that's like Steve was referring to as being the master, sort of, before, right? Like that's
the master would be part of the ROS2 instance, which is running on the cloud, yes.
Right. And the agent is the bridge between the ROS2 world and ROS then.
The agent is the bridge, yeah, between the agent is the bridge between the micro-ROS world and the ROS2 world.
Yeah. Sorry, that's what I mean. Yes.
The micro-ROS devices look like ROS
Yep.
devices. So we've got a little application running here that that is showing my two devices that I just showed you. There's also one called Alternative Facts, and that's basically just a test server. It basically starts at negative 40 degrees and then counts its way up. I'm going to restart it so we can see it go back to negative 40, because right now it's showing a temperature of 1100 degrees. But anyway, we use that for testing. And then I guess what we're going to show here is we'll have Brad show you his devices, and he will put them online, and we'll see them appear on the on the application.
Yeah, Brad, I'm putting you on the screen. Maybe if you want to show us the device.
Okay, so I'm going to change to my
Okay.
Yeah, there's devices. So here I have this is a Pico W with a BMP 280. This is a ESP32 with a BM 280, an ESP32C3 with an EMP 280, and an ESP with a SHT40. There's some photoresistors, GL5526s and 06s. But what you're seeing here is three different CPU architectures. You've got ARM, Extensa, and RISC. So I will turn them on, and if we can bring up Dave's GUI, or Dave's screen, it's going to take a little bit while they blink, but eventually they will, when they stop blinking, they will show up. There we go. So there's one. Oh, the Pico's working. Excellent.
And just so I don't think the question came already in the chat, but it might, like the sort of typical question about security and like, I guess in real life, we would be talking about the agent running on-prem, right? It's not like it would be something, and also for latency reasons, you probably would run everything on the factory, like on the shop floor.
Yeah, I
and not
think
necessarily in
the
this.
agent would be running on a
But-
robot someplace, but there's no reason
Right.
you can't do it the way we
Yeah,
are.
sure.
But
Yeah.
DDS does provide security if you want it.
Okay.
So
Okay. Good.
So there's my 3. Who's not there? Dave,
So
can
which
you
one are we
make,
missing?
make the thing bigger? It might be off the bottom.
Oh yeah, I guess the alternative facts one.
No. All right. So one of them's missing. All right. One of them. Oh, the this guy
Yeah,
didn't
you got
make
3.
it. I got 3, but I didn't get 4. So let me hit the button. Yeah, this guy's not there. All right. Let's see what happens. Anyways, he'll come up. He did before.
There's an
doesn't look like
interesting
he's gonna do
comment from Jan or John in the chat. The ROS versus ROS 2 split. It looks like not necessarily everyone has migrated just yet to ROS 2. That was actually one of the questions I had, because I know that the two have sort of coexisted for a while. As per the download statistics, ROS 2 is only just above
true.
Half, basically.
Okay.
Right.
Because there's a lot of deployment on ROS 1 still. And not everyone's going to upgrade to ROS 2.
Right.
But ROS 2 is continuing onward with development, whereas ROS 1 is in maintenance mode now.
Yep. Okay.
Yeah, sorry if I should have been clearer about that.
Yeah, that's fine. That's why we have also an audience and the ability for them to engage. So that's cool.
Okay, that's my piece.
All right.
Okay, so at this point, that's what Steve going to put his online, or I can come on to the.
So yeah, so some, if not all of the nodes are actually running, like except for the one with the alternate facts, which I guess is just a random like Linux client. Everything else is built with Zephyr, right? So like maybe you can dive a bit more into how this was done. So Steve, do you want me to bring you on stage and bring the screen, or what's next? Basically, you tell me, guys.
So I don't know if you had any. I don't know if your devices were ready to con on or not. I think I'll go on to the next part of the slideshow, which is
all right. Sounds good. And Oli is saying, so I was expecting that. That's really cool. We have lots of people from the ROS community. Oli is helping us also with more details regarding current status of ROS, the end of life for ROS 1. I'm not even sure it's called ROS 1. ROS is May 2025. So coming up in just about a year.
A little over a year.
Mm-hmm.
All right. So building micro-ROS, we found to be it's still difficult, and I think that kind of gets one of your earlier questions was how mature micro-ROS is, and it's still new. I'm not sure. Brad may want to elaborate, but I don't know if we're quite sure that it's ready for prime time, but I think I think it will be, because there is a need for something like this out there. But right now it's a little rough to build a micro-ROS system, and we had you do need to use PicoLibC. There's lots of warnings when you build it. Hopefully those will get cleaned up at some point, because a lot of times I find that I ignore warnings sometimes, and then real problems kind of get lost in all the noise of the warnings. In the code examples you see, we had to add just a dummy implementation of isatty because it needs it, but it doesn't really seem to be using it for anything, so we just always have it return 1. We are providing a script that we use that simplified building micro-ROS plus Zephyr, at least on the ESP32, ESP32C3, and on the Pico W. So that's out there on GitHub if anyone wants to go try it. We may also provide, can't promise, but we may also provide a Docker container to do the build, because we found that the build right now just is not as well insulated from your environment as things like just a West build of Zephyr is, or a Yocto build if anybody is used to using that in the embedded Linux world. It seems to be sensitive to a lot of environmental things, and we've seen that enough that I think it'd be valuable to have a containerized version of the build, but we're not quite there yet. But the installer should work if you have a clean Ubuntu 2204. It should definitely work. But if you've installed, other versions of compilers and things like that, then it could get a little iffy.
There's a question from someone on YouTube. Do you specifically use the micro-ROS Zephyr module, or like did you? Because I guess there was at some point, or there is like an actual Zephyr like West module, or like Can you elaborate on maybe what the script actually does? Because this person, I guess, tried a couple years back and was just discouraged.
Okay. Well, Brad is the originator of the script, so I think he may know a little bit more about the details of that.
So
let's bring Brad.
So out of the box, if you go to the website, you will get a Zephyr 2.5 build environment, which is lovely but not useful to us. So the things we did is we upgraded that to a 3.5 Zephyr build, but it is using the micro-ROS Zephyr module to build.
All right. Excellent.
Okay. So when we started talking about doing this demo micro-ROS on with Zephyr, there were three things we needed. Brad just alluded to one of them, which is we needed it to work with Zephyr 3.5, because I don't think you really want us giving tech talks about something that only works with an ancient version of Zephyr. So we need to get that going. And board with Wi-Fi support, but also enough resources for micro-ROS. The ESP32s were pretty ready to go, and we're good for that. But we also kind of wanted to be able to leverage the Pico W, because it has all the hardware. It's cheap. It's very popular. It has all the hardware you need to do this, but it didn't officially have Zephyr support yet for Wi-Fi. And also just more flexible I/O options, and the Pico W is good for that too because of the PIO. I am going to show some example code here. If you want to bring up my my screen. So in that the installer that we're providing through GitHub, it won't build the weather station app that we're demoing here, but what it will build is there's just a standard app called Ping Pong that basically just A publishes to B, who's subscribing to A, and B publishes back to A, who is subscribing to B. Just a back and forth ping pong, a typical ping pong kind of thing. So just want it's a pretty nice, simple micro-ROS app in Zephyr. So you have to define your agent's address. Obviously, you'd want to find a more dynamic way probably to do this in a production environment, but for the purposes of demoing and stuff, we hard-coded it as a config item. You have to declare publishers and subscribers, and then you basically define callbacks. Notice, so callbacks obviously for the type of the things you want to publish, but also for timer, for periodic events, you want to do those as callbacks through, and by what I mean by callback is it's going through micro-ROS's own scheduler, which is called the executor. And that's one kind of key thing that you really want to do when you're coding micro-ROS things. You want to use their scheduler. The first time I tried to do something periodic, I thought, oh, well, I'll just go spawn a thread in Zephyr and have it every 2 seconds go publish something and go to sleep. That didn't work very well because I think the code just wasn't designed really to be thread safe in that respect. And you might have been able to get it to work by putting locks in the right places and that kind of thing. But it's much easier to just use their facilities to do that. So that's one key thing is definitely if they provide a way to schedule something, do it through their scheduler. Don't try to do it through.
Yeah, I think that the same happens with, as far as I can tell, when building graphical user interfaces with a toolkit like LVGL, for example.
Mm-hmm.
It's the same. It's just easier to, when you want to have a part of the UI being refreshed every 10 seconds or so, there's a timer thingy in LVGL, and use just that and don't think about it too much. Yeah.
Yeah. So then in the main routine, you have to do a little bit of setup. You have to set up some functions, and then it's mostly initialization of various things, and you have to read through the API docs to get the flavor for that. But once you've done all that setup, you basically get down here to. And this is even more complicated than it really needs to be. So it's really just a while one loop that that runs the executor. There's no reason they even need to have that spin some, leave, and then sleep thing. They could just run the. There's an executor call that just kind of does that for you. And they've got some stuff below the while, but I don't see any way you could ever actually get there, since there's not a break in the in the while loop. But you really are supposed to call these finite finish functions to tell the server you're done. I suppose that seems like that would be hard to me, honestly, on a small system like this, because a lot of times, people may just like pull the plug. You can't always guarantee that you're going to be able to send those, but they are there. And then there's the fake is a TTY. So pretty simple for just a simple publisher app. And then I also wanted to show the server and the client for the weather station that we're using. That gets a little bit bigger. So we have to set up the network stuff. And again, it's hard coded. And then you'll see here that in the server, we actually have individual callbacks for each of the different types of data. So the light, the temperature, the humidity, the pressure. And those are so that you can support the client server interface, where you may just want to just go get the temperature. For pub sub, we just have this anybody out there that basically just tells everybody else on the network, like, publish what you have. And when they do that, they publish they would publish everything all at once. All the temperature, the light, the humidity, and the pressure. So is there anything else interesting there? Probably not a lot. We will get to the bottom, and there will be yeah, so see here, we didn't even need the while loop, because we just called executor spin, and that basically just goes on forever. Unless there's I guess the exception, the reason you might want to do it this way rather than the while loop is if there is some kind of exception or something, you would eventually be able to call those finish functions, because you're not stuck in a while loop. And then there's the client program. The only thing I really wanted to show here was the bottom, where it just shows an example of so is basically just a request to get the temperature. So you can do that individually with the service interface. So so that's about it for the for that part of the code examples. Can we go back to the slideshow?
There you go.
Okay. So the code examples. So I also wanted to talk a little bit about the Pico W and Wi-Fi. So I realize we're kind of running short on time, so I'll try to be quick here. The Raspberry Pi Pico W does have a Wi-Fi module, but it's not officially supported by the Zephyr tree right now. Infineon has put in a driver that supports the chipset, but only with a SDIO interface. And when we had started doing this, we weren't actually aware of where that effort was. I think we were kind of vaguely aware it was going on, but we weren't aware of what it was. So we had kind of just started down our own path, and we'd build a Zephyr driver based around the same Wi-Fi driver that's used in the Pico W SDK, and for the regular environment that people use with Pico W, where there's no operating system, that kind of thing. It's actually got a fairly nice generic driver that was reasonably easy to plug into the Zephyr API and into the Zephyr IP stack. Eventually, we'd probably be able to do this with the Infineon driver, but right now we have one that works, that interfaces with the SPI PIO that plugs into the Zephyr IP stack, and the URL, which I think Benjamin's going to post to the top of the YouTube link once this tech talk is over. If anybody wants to look at it, it just the repository you get here will basically just do an out of tree build of a generic Zephyr environment with the network shell and the Wi-Fi driver built in. So if you want to do Wi-Fi on your Raspberry Pi Pico W, you can use that. Okay, and Steve wanted to talk a little bit about the PIO, because he was the one who really got in and did the PIO part of that work. And so I'll pass the slideshow to him.
So Dave, can you drive the slides for me?
Yes.
Back to the slides for a moment. So back in ancient times, when you wanted to build something around a microprocessor, you had the microprocessor chip, like an 8080 or later on a Z80. And then if you wanted to, say, do serial communications, you added a UART chip, which was a separate chip. And I2C and SPI hadn't been invented yet. But nowadays, that's all built into the SoC. So there are limits, of course. A typical SoC has some number of UART devices or I2C devices or SPI devices. In this particular case, the RP2040 has 2 of each. Oops, back a slide.
Back. Sorry.
Not yet. Another thing to keep in mind is the pin assignments for those. Even with a pin multiplexer, there's only specific mappings that can be used, for example, on the RP2040 for the UART or SPI. Now the next slide. So the RP2040 introduces a new programmable I/O block, and there's 2 of those on the RP2040. The programmable I/O is controlled by program instructions dynamically loaded by the CPU. It's a very limited instruction set, and there's only 32 bytes or 32 words, I'm sorry, of program memory, but it's specialized for I/O, and there are control registers that give you very, very flexible configuration for the PIO. On to the next slide. Each of those 2 PIO devices has a program memory for 32 instructions, so they're completely separate. And it contains 4 state machines, which execute the instructions. Each of those state machines has an input FIFO and output FIFO, each of which is 4 words deep. It has input and output shift registers. For example, if you're doing serial communications like SPI or I2C or even a UART, you feed the data out through the shift registers. There's also a couple of scratch registers that you can use for counters and so on. The PIOs run at system clock speed. So each PIO instruction can be executed in as little as one instruction. One of the fun things about the PIO is you can have complete control over the IO pins on the RP2040. You can have you can send out, you can set all the IO pins in one instruction in one clock cycle, which can be pretty impressive. But you can control the speed at which that happens with the clock divider to slow it down to, say, the baud rate that you want. There's also some internal counters that track where you are in the shift register, for example. So if you go on to the next slide. So the control registers let you set up a bunch of things. You can define what the input pins are, what the output pins are, the shift for the input and output, which is, for example, how many bits the shift registers move after you do an input or output operation. There's also a concept of a side set pin or side set pins, where you can set other pins separate from the input pins and output pins. You configure the clock divisor. There's also a wrapping concept. For a simple program, you might have a jump instruction to jump back to the beginning. Program wrapping lets you specify a start address and an end address. And if you hit the end address, it wraps back to the start address. So you don't have to add that jump instruction, which can save you memory in that program memory. So do we have, next slide. So here's an example taken directly from the Pico SPI driver that's already in the Zephyr main. And Benjamin, can you switch to my desktop display? Here it is in situ, in place, where we've got one of the glitches is the PIO assembler is not available as a package that can be used directly in Zephyr, in a Zephyr build. So you have to embed it as binary. The assembler adds these comments for you, which contain the original code. I have that original PIO code right here in the next window. So this is what PIO assembler looks like. Defines a program for SPI mode 00 and for SPI mode 11. It defines a side set pin. So the way this is set up, there's one output pin defined, one input pin defined, and those are separate pins. There's also a side set pin defined, and I'm using that side set pin for the SPI clock. So these two instructions are a complete SPI program for the PIO. And this is the main for the BME 280 sample. And this is an unmodified sample from Zephyr in samples, sensor, BMI 280. And this is the overlay file, which I'd added, which defines the pins. Benjamin, can you switch to my desk camera? Yeah, that. Those of you intimately familiar with the Raspberry Pi Pico might notice that this is not the standard pin assignment for SPI. The default on that device is pins 21 through 25. Instead, I've got it over here on pins 16 through 20, and it's talking to a BME 280 chip. I think that's all for that. So back to the desk display. And that data is coming back through here, reporting temperature and pressure and humidity. And that's the straight BME 280 sample with this overlay file. What I've done is define a PIO SPI 0 default pin configuration, assigning pins 14 and 15 as outputs and pin 12 as an input. Scrolling down to the PIO definition, there's a PIO SPI device under the PIO, and under that there's a BME 280. And defining the chip select is pin 13, clock is pin 14, the GPIO master out slave in is pin 15, the input from the device is pin 12, and that's how it's set up to work. I think that's about all I need to show for this. So
nice. All right. So how about we go back to the ROS aspect of the demo, maybe, because I think we've seen sensors and data flowing between the various nodes. But I guess at some point it makes sense to actually have it have a manifestation in the physical world, right? So Dave, I think it's you who has the demo setup, right?
I will turn on
one more thing to show.
Sure.
Not that one.
What do you want me to show?
Dave, were you going to show the...
Oh, okay. I thought you said you wanted to... all right. So I'm going to turn on my camera here, and you'll probably all move a little closer, I guess, to this, and I want to put it on full screen. So, that's blurry, isn't it?
It's all right. No, it's good.
Okay, that's pretty good. So what I did was, I don't know if you knew, if you remember, but I mentioned that one of my temperature sensors was outdoors, and it's about, I don't know, it says it's about 7 or 8 degrees Celsius outside today in Boston. And I just brought that board in. And so 2 things to see here is one thing that's cool is I'm running on 2 AA batteries. And that's something you couldn't do with a ROS 2 instance very easily, I don't think. And that sensor I've connected to this little Lego power-up robot set. And these are basically just analog gauges. This one here represents the pressure, which isn't going to change a lot. The temperature, we should see it ticking upward every few seconds. I may have timed this poorly. I just brought it.
Well, you can probably I don't know where the sensor is, but putting your finger on it might.
You can do that, yeah, that's true. Let's see if we can accelerate it. I'm putting my finger on the sensor right now. Okay, yes, and we can see it moving rather fast, yeah. So it's going to work its way up. I think I defined the upper range to be 25 degrees, something like that, and my finger's probably going to get it there pretty quickly.
And that's where the ROS sort of way of approaching things could kick in, where like right now there's sort of a one-to-one mapping between one sensor and one gauge.
Yeah.
But you could have other nodes like computing automatically, like
you could,
averaging the data or like going through random algorithms.
Yeah, and my initial whack at this demo, that was what I actually was doing, was just doing a moving average of everyone's. And then we kind of discovered that, well, like, unless we all simultaneously like heat up our sensors, it's not going to make for much movement. But in the real world, yes, you could definitely use this to aggregate data from all over the place, or, you know, you can certainly imagine robotics applications where you're pulling in data from lots of different LiDAR sensors and assimilating that into, you know, something that one robot motor responds to or something. So just wanted to show that at the end, just to you know, kind of complete this, because the emphasis here really was on the communications infrastructure. But when you're talking about robots, you have to show some kind of robot, I think. So this is what we did.
All right, awesome. Let me see. I'm going to bring everyone back on the screen, because I think we should probably take some time to go through questions. I think someone mentioned, usually we do take the questions as they come. Someone at some point, I think, said that they'd rather we go uninterrupted, which we did. But now is probably time to catch up on some of the questions. There is one from Bayram if you look in the micro-ROS repo, it states that the latest version that's supported, at least officially, I guess, is 3.1. But you guys mentioned that you're running on 3.5, right?
Right. We intend to submit those, but Dave and I only finished getting the bugs out Saturday, and Sunday, so we haven't really had time to package it up and ship it off.
All right. Yeah, makes sense. Let me see. Am I missing other questions?
There was a question about micro-ROS to micro-ROS, and Dave's demo is a micro-ROS to micro-ROS, where the sensor is talking to a micro-ROS controller.
Right. Sorry, I misclicked because it moved. Yeah, but you still need the agent.
You still need the
right?
agent. Yes.
The agent has to be there, but the micro-ROS devices can certainly talk to each other just as if they're almost as if they're ROS devices.
Yeah.
So the agent
handles. Whoever described this as peer-to-peer and like BitTorrent earlier in the comments, I guess that's reasonably close, right?
The agent handles addressing and resolution of where things are.
Speaking of, I guess there's this interface and RPC sort of interface between micro-ROS and ROS2. How tightly coupled are micro-ROS releases with ROS2 distros? And do you need much versions?
You can build micro-ROS on anything. We've got it up on Iron as well. But just like ROS, you need to make sure that if you're running ROS nodes, well, they probably should all be at the same release level. And same thing, if you're running humble ROS nodes, you probably want humble micro-ROS. If you're running Iron ROS nodes, you probably want Iron micro-ROS.
Right, makes sense. So I think it was Steve who mentioned in passing that out of the 4 devices, one was RISC-V. Javier is asking if you've done any work with RISC-V, micro-ROS, and Zephyr, and if you have any thoughts, I guess, and what do you think about this particular setup?
So the ESP32C3 is a RISC-V. It works. I mean, what can I say? It has its little quirks sometimes, but we've got it running.
Right. Makes sense. That's good enough. Oli, what's next in the development pipeline for Zephyr micro-ROS development? I guess, like you said, maybe contributing some patches upstream to micro-ROS so that there's it's more aligned with recent versions of Zephyr.
Right. And we probably should try 3.6 when it comes out, just for giggles, since that stays away.
Yeah, and getting to the point where so we have this notion in Zephyr where some modules would be like whenever you check in Zephyr for the first time, modules like LVGL, like I was mentioning, you would sort of get them automatically. But we have also, like in the Zephyr main manifest, there's a set of optional modules, like TensorFlow Lite for microcontrollers and like a bunch of others. It would be nice to have micro-ROS there so that whoever wants to sort of opt in to getting micro-ROS in their workspace could do so. Like I think that would be nice, especially if the version ends up being aligned with,
That might be a little tricky because in order to build micro-ROS, you need a full ROS installation.
Yeah, I remember that now that you say it. Yeah, true. All right, I think that's more or less it for questions. I mean, we still have a couple of minutes left. Just want to make sure that I make a quick plug for what's going to be next. So we're going to be back in 2 weeks' time with a talk that's already been published. I don't think I've prepared the visual to put it on screen, but you know the drill. Like you just sign up on LinkedIn or on YouTube. The topic is going to be we're going to have Louis, who I think is watching today, telling us about how he added support for Bluetooth Low Energy as a backend, a transport for using the Zephyr shell. So that's going to be quite interesting. And I think right after that, we are talking basically last Wednesday of February. We're going to be a few days after the 3.6 release that you guys were referring to. And we're going to have a release party like we did the last time, bringing a bunch of maintainers and release managers to talk about what's new. And there's actually quite a few things. Javier, where can we find the code and slides of the talk? So hopefully Dave and team, you can, like if you want to shoot me a PDF or like put a PDF somewhere online, we can certainly link to that. And the code, the COBOL repos, I will also make sure that you find the link in the recording. Like if you might actually already be watching the replay on YouTube. If that's the case, then the links would be already in the comments, in the description.
Make sure the links get there.
We will get them. John/Jan, was that the ESP32C3? Yeah, I guess that's
Yes.
That's one of those.
Yep.
all right. And with that, I think that's a wrap. We have people who are going to give micro-ROS a try.
Compliments.
So I think I have a few old demos myself. So I think I was using Serial and not Wi-Fi/UDP back then, but I will look into using them again. Rob, thanks. So does Naushad, and probably a few others as soon as we will be off the air. Feel free to subscribe to the YouTube channel, like the video to make sure that you don't miss our next Tech Talks. There's one, virtually every week, every other week. So we will be back shortly. And with that, thanks Dave, thanks Brad, thanks Steve. It was great. The demo worked, so that's usually a good indicator. And
thanks for hosting us.
Things. It was a lot of fun, and we'll see you all in 2 weeks. Bye.
Bye-bye.
Bye.